Hey, Professor Cam. Just wanted to say hey and answer the questions for the oral exam. Here we go. For the first question, you were asking about disinfectant for the hospital. So it was an optimization question, and you didn't actually want us to answer it, but I think you were more concerned about um, knowing what or how we would approach the problem if we were to have to solve it. So for that, it's going to be obviously an optimization problem. And probably the thing that we're going to want to optimize is we're probably in optimization problems, you're either looking for a minimum or a maximum value. Um, so for this problem specifically, we would probably be looking for a minimum, and it would be a minimum amount of either money that the hospital has to spend on disinfectant, or it would minimize the amounts of disinfectant, the amount of gallons of disinfectant that the hospital has after a normal day's use. Um, because a lot of times optimization is concerned about profit. So in the hospital's case, they're not going to want to spend more money than they have to. So we would want to minimize the amount of leftover bottles of or gallons of disinfectant that they have on a daily basis. So what we would want to do is come up with some function or relation that describes two things. The first is that is the number of bottles of disinfectant that they have on hand at any given time, and the second part to that would be the rate at which they go through the bottles, or the number of bottles they go through for a given time period. So if it's a day, they go through X number of gallons of disinfectant, and so forth and so on. And once we have that relationship set up, then we can start our calculus and our optimization. We could differentiate the function and set it equal to 0 to find the critical points. We would want to find where that function is at a minimum, so we would be looking for the value where it stops decreasing and starts increasing again if we were to look at it graphically. And at the end of the day, what we'd be looking to do is to minimize the amount of bottles of disinfectant or gallons of disinfectant that the hospital has at the end of a given workday. And by minimizing that, we would maximize the hospital's profit because we're not taking away money for extra cleaning supplies that are just sitting in the cupboard somewhere. So that would be probably the best way to go about solving that problem. So for the second question, you were talking about the fundamental theorem of calculus and the relationship that it expresses between the slopes of tangent lines and the area under curves. And you kind of just wanted us to talk about that a little bit, about the relationship. You said a little bit about the context of the position and velocity graphs. And it's actually interesting that you mentioned that because I just finished my physics exam yesterday for the semester. So it's really interesting to see how physics and calculus, when you're at a collegiate level, overlap. Looking at position and velocity in particular, a lot of people know in calculus, yeah, it's just the derivative. But when you go to physics, you can actually see that application. And so it's really cool knowing that if you are able to graph the position of any object as a function of time, if you look at any point on that and you can take the derivative of that point and get the slope of that line, then you know exactly, if you were to graph its velocity, how much area would be under that velocity curve. And it's really cool, and you can do it the opposite way too. If you have a velocity function plotted against time, you can take the area under that curve and you can figure out how much distance was displaced from 0 to that period, or on whatever period you're looking at from A to B. And so it's really cool, the relationship that the fundamental theorem has, really, when you just realize that it's been undoing everything we've been learning to do pretty much the whole semester with derivatives. But it's really invaluable to have that tool in your toolbox to realize that you can go jump back and forth from a position to a velocity graph and still know what you're doing. Knowing that as much as velocity is the derivative of position, position is the antiderivative of velocity, and you can find that with an integral. So those are kind of some cool insights to know and to realize. that even if it's not a straight line, even if it's some wacky curve, that you can still get a lot of valuable information about that. Is really helpful. So for your third question there, you asked us about the last problem on the exam. I think it was actually the 7th one for me, the second to last one. But I only remember that because I looked at it, I took one look at it, and I was like, oh no. So I skipped it, I went to the next one, and then I came back to it once I had some extra time at the end. And it was kind of scary when you're looking at it, but once I made that connection in my head, like, hey, that looks like a quotient rule, it was really easy to isolate like F and G if you were to break them apart and to get that that function or that representation of what the function would have looked like before we took the derivative. So it was kind of cool to see that, and making my own problem was kind of fun, I'll admit. So my problem I got set down here. I don't know if you can see it, so I'll try and explain it as best I can in words. It's the integral of 2 times this whole expression. So it's cosine of e to the x plus 4 times negative e to the x plus 4 sine of e to the x plus 4. So got some e to the x's floating around, got some trig stuff floating around. And if you look at that at first glance, it could kind of be freaky. But if you separate that into 2 parts, kind of like if you had 2a, you could do a plus a. If you were to separate that into 2 equal parts, then you can actually realize that it's actually just a what you would get if you did a product rule. So you have one thing plus another thing, or 2 things multiplied together plus another 2 things multiplied together, I guess is a better way of explaining it. So all this stuff is the calculus differentiating in the middle, and what you work back up to up here is just this expression cosine squared of e to the x plus 4. So that's the answer to the problem if you're differentiating. Anti-differentiating, if you wanted to differentiate this function, you would get this expression down here at the bottom. So I had some fun doing it, messing with squares and like simplifications. But if you take this out into cosine down here, cosine of e to the x plus 4 times cosine of e to the x plus 4, and then you just have a couple chain rules to do, and then you're on your way to becoming a master at calculus. So I did have some fun with that, and that was the problem that I did there. Probably could have done some other crazy stuff, but just for the sake of the video, so it's not 30 minutes long like you were saying in your description there, I'll go ahead and jump to number 4. So number 4, I think, is just kind of a fun question. You asked what our favorite number is and why. My favorite number personally is the number 8, and that holds true for a couple different reasons. The biggest reason is that I guess it's more of a personal reason. I grew up in a different school district from the school that I graduated from. I originally grew up in the town of Fenton, so I went to school there from kindergarten to 6th grade. And during that time, I played t-ball, I played baseball, right up until the time that our family moved. And during that time, the number 8 was actually the first number on the back of the jersey that I got to wear. And it was actually my jersey number from t-ball when I was 4 or 5, all the way up until 6th grade, before I left and moved to Swartz Creek. And then after I moved to Swartz Creek, the first year I was there, it was kind of different. And it was actually kind of symbolic too. It was kind of funny. The first year I was there was my freshman year. Or it was actually my 8th grade year of middle school. There's a little bit of fuzzy time in between. But I got there in 8th grade, and my number in 8th grade was 25. So it was totally different baseball number on the jersey, totally different school and atmosphere. But my freshman year, moving into high school, I got that number 8 back. So it was kind of like everything came full circle. Things were starting to get on my side again. So it's just kind of a personal touch. Everybody has to have a favorite number, so that's kind of the story behind mine. But I hope that I did all right answering those 4 questions, that you could follow me. I know sometimes my intellect is kind of like Vincini from The Princess Bride. It's a little dizzying, but hopefully you could follow along. And I just want to say thank you again for all of the hard work you've done this semester. I know you probably heard a lot of students griping about how hard it's been. but we don't want to discredit what you and other professors have been doing, because I know that you've been doing a lot of hard work trying to change all of your curriculum over into something that would work in an online format. So I want to say thank you again for making this more of an enjoyable experience than it would have been on its own. So just wanted to thank you for that, and hopefully you have a great summer. Hopefully we can see everybody on campus, keyword see everybody, next semester. But thanks again for an awesome semester, and best wishes in the future. Thanks.